You know, some problems in calculus can feel like an absolute beast to solve. But what if I told you there's a tool that can turn a nightmare problem into something, well, almost elegant? Today, we're demystifying triple integrals in cylindrical coordinates. Let's get into it. Have you ever tried to do that, fit a round peg into a square hole? It's awkward. It's clunky. You're just forcing something that clearly doesn't belong. It just doesn't feel right. Well, believe it or not, that's a perfect analogy for what we sometimes do in calculus. Yep, trying to describe something that's naturally circular, like a cylinder or a cone or even the dome of a building, using our standard, boxy XYZ coordinate system is basically that same problem. You can do it, but the equations get ugly fast. The integrals become these horrible, complicated messes. There has got to be a better way, right? And of course, there is. Here's the good news. If you're already comfortable with polar coordinates in 2 dimensions, you are like 90% of the way there. All we're going to do is take that familiar polar system on the flat xy plane and just add a z-axis, a third dimension for height. That's it. So these are the formulas that make it all happen. We swap out our x's and y's just like we did in polar. X becomes r cosine theta and y becomes r sine theta. But what about z? Well, this is the best part. Z just stays Z. It doesn't change at all. It just handles the up and down while R and theta take care of the circular part on the floor. Simple. So when we put it all together, this is what our fancy new triple integral looks like. You can see we've swapped out the x's and y's inside our function. But hold on. Look closely. There's an extra little something in there. Do you see it? It's a single letter, but it is the absolute key that makes this entire system work. It's this extra R. That's the secret sauce. Our tiny little chunk of volume, our dV, isn't just dz dr d theta. No, it's r dz dr d theta. You can think of this r as a special adjustment factor, because a small wedge of volume near the center is way smaller than a wedge out at the edge, right? This r perfectly accounts for that difference. It's the price of admission to use this much easier system. And I really, really cannot stress this enough. Seriously. Forgetting to multiply by that extra r is, without a doubt, the #1 mistake students make with these integrals. So if you remember one thing today, let it be this. When you go cylindrical, you have to pack that extra r. Now, let's see this thing in action. All right, first up, let's find the mass of a cylinder. Its base is the circle x squared plus y squared is less than or equal to 4, and its height goes from 0 to 3. Now, what's interesting is that the density isn't the same everywhere. It gets heavier as you go up. The density is just equal to z. First things first, we need our bounds. So because we're dealing with a full cylinder, our angle theta is going to swing all the way around, from 0 to 2 pi. Next, the radius. The equation x squared plus y squared equals 4 is a circle of radius 2. So in our system, r squared equals 4, which means r goes from the center at 0 out to 2. And finally, the height z is given to us straight up, 0 to 3. Easy enough? Okay, time to build the integral. We slot in our bounds, z from 0 to 3, r from 0 to 2, and theta from 0 to 2 pi. Our density function was just z, so that goes in. And then, what's the one thing we can't forget? Our extra r. And there it is. Believe it or not, the hardest part is over. Now we just have to solve it from the inside out. So we tackle the innermost integral first, the one with respect to z. At this point, we just pretend that r is a constant. The integral of z is z squared over 2. We plug in our bounds, 3 and 0, do the subtraction, and that leaves us with 4.5 times r. See? 1 layer down, 2 to go. Next up, the middle integral. We take that result, 4.5r, and now we integrate with respect to r. We evaluate that from 0 to 2, and what do you know? We get a nice, clean constant, 9. And for the final step, we just have to integrate that constant, 9, with respect to theta from 0 to 2 pi. And that gives us our final answer for the mass of the cylinder, 18 pi. Done. Okay, ready to level up? Let's try something a little more interesting. We're going to find the volume of a solid that's sitting on the floor, the xy plane, and it's capped by this beautiful dome shape, the paraboloid z equals 16 minus x squared minus y squared. This is a perfect job for cylindrical coordinates. All right, let's figure out our bounds. Again, it's a full symmetrical shape, so theta goes from 0 to 2 pi. Now for z. The floor is z equals 0. The ceiling is the paraboloid itself. And what's x squared plus y squared? It's r squared. So our upper z bound is 16 minus r squared. Notice that our height now depends on how far we are from the center. Finally, to get the radius, we ask, where does this dome hit the floor? We set z to 0, which gives us r squared equals 16, so r is 4. Our radius goes from 0 to 4. So here's what our integral looks like. Now, since we're finding volume, the function we're integrating is just the number 1. But we still can't forget to include our extra r. See how that upper bound for z isn't a constant anymore? It depends on r. That's totally normal, and it's what makes the system so powerful. Just like before, we start from the inside. We're integrating r with respect to z. That just gives us r times z. Now we plug in our top and bottom bounds for z, which simplifies down to a new function we need to solve, 16r minus r cubed. On to the next layer. We integrate that result with respect to r from 0 to 4. A little bit of polynomial integration here, plug in the numbers, and the math works out to a very satisfying 64. And for the grand finale, the theta integral. Integrating the constant 64 from 0 to 2 pi gives us our final answer. The volume of that entire paraboloid is 128 pi. How cool is that? We took a complex 3D shape and found its exact volume with just a few pretty manageable steps. That's the power of choosing the right tool for the job. So let's wrap this up. What are the big takeaways? First, if you see a problem that has anything to do with circles, cylinders, cones, or you see that x squared plus y squared term floating around, a little bell should go off in your head. Think cylindrical. Second, the conversion itself is a piece of cake. It's just polar for x and y, and z gets to just be z. And third, and I'll say it one last time, never, ever, ever forget to multiply by that extra r when you set up your integral. So there you have it. You've now got this incredibly efficient tool in your calculus toolkit, one that turns these messy, rectangular nightmares into clean, elegant solutions. The only question is, what problem are you going to solve with it next?